Hello everyone, myself Professor Tushar Gujrati from S&T College of Engineering, Yeola. Today we'll study the control systems. So control systems, basically there are three control systems are available: P, I and D control actions. So P is proportional, I is integral and D is derivative. So these systems are acts independently also and they act combinedly also. So we need to understand all the three systems carefully. So let's try to understand this. So I have just shown you the PID control action. So if all the three control actions are combined together, then it is called as PID control action. So in this diagram, this is the controller, PID controller. Okay. So here all the three control actions are combined together. So input to the system is error and output is control signal. Okay. So the full form is proportional, integral and derivative control. Okay. So now in order to understand this combined control action, first of all we need to understand it separately. Okay. So what is proportional control? Okay. So we need to understand first of all what is proportional control. So proportional control, the control signal is directly proportional to the error. Okay. So just we understood that the controller has input is error and output is control signal. So input is E and output is U. Okay. This is the proportional controller. So the equation for proportional control is u of t is equal to up of t. So p is here for proportional, so up of t is equal to kp into e plus offset. Okay. So just we understood this statement that u is directly proportional to e. Okay, u is directly proportional to e. That's why if you remove constant of proportionality, then u is equal to kp into e. Okay, this is the equation, u is equal to kp into e. So actually everything varies with respect to time, that's why it is written in terms of time. up of t is equal to kp into e plus offset. So this is the proportional control action. So what is written here? As the gain is increased, the system responds faster. The system responds faster to changes in set point, but becomes progressively underdamped and eventually unstable. So here this kp is called as gain. This kp is called as gain of the controller, or it is called as constant of proportionality. So kp is called as here constant. So now we try to understand this equation. Suppose this error is 0, e is equal to 0. What will happen? The output is constant, that is output is also 0, that is u is equal to 0. Okay, because error is 0, that's why this term gets 0, and this offset will not produce, therefore u is equal to also 0, output is 0. Okay, and if the error occurs, what will happen? Then for every 1% of error, what will happen? Correction kp percent is also added or subtracted from p0. Okay, so like this correction continuously occurs. If error changes from 1% 2%, at the same time what will happen? The control signal also change proportionally. Okay, so this happens over here. And here offset is present as a error. So though system works proportionally, but there is some error in the system, that is called as offset. Okay, so here as gain increased, system responds faster to changes in set point, but it becomes progressively underdamped and eventually unstable. After some time the system becomes underdamped and eventually unstable. Okay, unstable system occurs after some time period. This is the disadvantage. So here the graph is shown how proportional control action occurs. So here the input is error. Okay, here input is error, that's why it is shown on y-axis, and x-axis is time. So suppose error varies something like this in step form. Okay, then the output of proportional controller should be something like this. Okay, but as time proceeds, because of some offset, it may get like this also answer. Okay, so like this proportional control action works. So it works proportionally to the input. So advantages of proportional control action. What are the advantages? It is simple and easy to design and tune. Actually, it is very simple and it is easy to design. It's rapid response and it reduces rise time. It reduces also steady state error also gets reduced with the help of this system. So in short, this is relatively stable system. Okay, and it provides good stability. And what are disadvantages present over here? It is not possible to eliminate steady state error or offset. So there is offset is present and we cannot eliminate offset here, and this could lead to instability, that is rise in overshoot oscillations. So this system can increase oscillations also and overshoots also. So the application of this system is float valve, thermostat, etc. So these are the application of these systems. Okay, now we'll study the another system that is called as derivative control system. So what happens in derivative control? It produces a control signal proportional to the rate at which error is changing. So here we have to take error of the derivative of the error. So here error is changing with respect to time, and we have to take the rate at which error is changing, that is dE by dt. Okay, this is dE by dt. So that's why equation is derivative equation. Okay, so dE by dt. Now here the constant of proportionality is kd. Okay, so it is called as kd. So here kd is called as derivative time. Okay, so this is called as derivative time. So as you write that u is directly proportional to dE by dt. Okay, so if you remove constant of proportionality, then it will be u into k into dE by dt. Okay, so like this is there. So derivative control produces a control signal proportional to the rate at which error is changing. It is also known as rate controller. Okay, so while sudden or rapid change in error leads to a control signal of large magnitude, gradual changes leads to a small magnitude. Okay, so you understand this concept. If there is rapid change in error, that is d by dt is rapid change in error, then what will happen? There will be larger magnitude. Okay, and if there is gradual change in error, then there is small magnitude. Okay, even if the error is huge, the derivative control will generate no signal if the error is constant. Okay, if the error is constant, okay, the derivative of constant is 0. Okay, that's why it will not generate any error. So there should be some change in error if we want to generate control action. Okay, so if error is 0, what will happen? There will be no control action. Okay, that's why the error should be continuously varying to generate some control action. Thus not used alone, it is used with proportional controller. Therefore this control is used along with P controller. Okay, so this is the diagram here. So here error is changing, so you see the slope. Okay, the slope tells us whether error is changing or not. So because of slope we understand the error is changing, therefore it generates output for the same time period. So we get output for the same time period, that derivative action is generated when error is changing. So this is the graph. So advantages of derivative control action. What are advantages? It reduces settling time. It also adds lead. Okay, so settling time gets reduced with the help of this derivative control. It reduces overshoots, add more stability. So overshoot is reduced with the help of derivative controller. Okay, and there are some disadvantages are also not possible to eliminate steady state error or offset. So offset cannot be reduced with the help of this derivative control. Not possible to use alone. We cannot use it alone. Excessive use may make the system slow. The system may get slow because of excessive use. It amplifies noise. Noise gets amplified. An application is in conjunction with P control. We can use it with in conjunction with P control. So these are the advantages and disadvantages of derivative control action. Now we'll study integral controller. So what is integral controller? Now the name indicates, what name indicates? There should be integration of error. So here you see, here there is integration of error takes place, and Ki is nothing but constant of proportionality. Okay, so that is called as constant of proportionality. So Ki also called as integral time. So Ki is called as integral time. So here again U is output, control signal is output. So here rate of change of integral control signal is proportional to error. So control signal proportional to integral of error. You remember this point, that is control signal is proportional to integral of error. So now when the error is 0, what will happen when the error is 0? The control signal is constant value. Okay, the control signal is constant value, and the error is, when the error is constant, the control signal varies at constant rate. So you remember these two concepts. If you take, suppose when the error is 0, if error is 0, what will happen? The control signal is constant value, and when error is constant, the control signal varies at constant rate. So here you check now, when the error is 0, when error is 0, what will happen? Just we read, the control signal is constant value. Okay, and when the error is constant, the control signal varies at constant rate. So here the error signal is constant like this. Here is constant, that's why error varies, okay, at constant rate. So when it is constant, then it varies with particular rate, and when it is 0, okay, here it is 0, at that time it is constant. Okay, so like this you remember, when error is 0, we get some constant value like this. So like this integral control action works. So the advantages of integral control action is, it eliminates steady state error or offset. So it eliminates steady state error or offset. It decreases rise time. Rise time gets decreased by this integral controller. What are disadvantages here? It causes integral wind up. Okay, it leads to minor increase in overshoot. There is minor increase in overshoot. It could make the system less stable, increases settling time. So these are some disadvantages, and its application is, we can use it in conjunction with P controller. We can use it with P controller. So these are some advantages and disadvantages of integral control. So just now we saw all the three controllers. So each controller has different control actions and different advantages and disadvantages. So if we use properly combination of these controllers, then we can reduce the errors properly, overshoot we can reduce, and we can get proper stable conditions. So this is one point is there, integral wind up. This is for advanced learning purpose. So it is caused by actuator saturation. So as we use actuators, so because of saturation of actuator, this error occurs. So what happens in this case? Feedback loop is broken and the system runs in open loop because the actuator remains saturated. So here feedback loop gets broken. So while the error is 0, the integral term will keep building and becomes very large over a period of time. This in turn will lead to saturation of control signal. Okay, so if feedback loop is broken, what will happen? The error is 0, and because of this, the integral term will keep building and become a very large over a period of time. So the condition will prevail even when the error changes, and it may take long time before the integrator and the controller output comes inside the saturation range. And because of this, what happens? The controller output gets in saturation range. the consequence is that there are large time delays. Because of this, there is large time delay occurs. So this is the drawback of this integral wind up. Because of this, what we'll get large time delays. So thank you so much all of you for watching this video. In this video we covered the PID control actions working separately. Okay, so thank you so much all of you.